There are two new equations I've added to the equation sheet this year for the position of an object in simple harmonic motion that we really didn't get any time to really get into. So this is just a quick little introduction or quick explanation for it all. So your position is going to be followed by one of these two equations. Your amplitude times the sine of 2 pi times the frequency of the motion times the time that we're looking at, the amount of time that has elapsed, or your position will be your amplitude cosine 2 pi frequency versus time. If it's a sine curve, obviously it would look like this, or the reverse, or the negative one would look like this instead. So you would use that equation if that was the way the graph looked, or if it was a cosine one, we'd be looking at this one if we started with positive maximum displacement, or if we started with negative maximum displacement instead. The other thing is, depending upon where you're starting, if the object is starting in equilibrium, then you're going to most likely be dealing with a sine curve. If your object is starting at maximum displacement, then you're going to be dealing with your cosine curve instead. So it just depends. So let me give you an example of something that might be true here or might make sense. So let's imagine we've got a spring mass, spring attached to a wall, and it is stretched out to a maximum displacement with a block. The block is, let's say, 0.5 kilograms. And here is its equilibrium location. So basically, it is now at a location that is 20 centimeters away from equilibrium. And we were trying to determine the location after 1.5 seconds. Where would it be located? So again, this would be following simple harmonic motion. Since it's a spring, the period of a spring follows 2 pi square root of the mass divided by your spring constant. Let's say the spring constant was 10 newtons per meter. So we can go ahead and find our period. That'd be 2 pi. The mass that we're lugging around is 0.5 kilograms divided by 10. And if we did all that, 6.28 times the square root of 0.5 divided by 10, the total period on this would be 1.4 seconds. 1.4 seconds. So let me make a little change to this. Let's say after 2 seconds. 2 seconds, where is it going to be located? So why did I find the period? Well, the period is going to lead you to your frequency. Frequency is 1 over the period. So 1 over 1.4, we have a frequency of 0.71 hertz. So that means that every second we're completing about 71% of a oscillation. It takes us more than a second to complete it all together. So basically, again, for it to go all the way to equilibrium and then 20 centimeters to the left and then go back again to equilibrium and then back to its maximum displacement there, it's going to take 1.4 seconds altogether. We're trying to figure out where is it going to be located at the 2 second mark. So obviously it's going to be on its way back in this direction at the 2 seconds. So it'll be maybe closer to equilibrium, which again is always going to be a value of 0. Maybe it'll be negative. We shall see. So if we follow our formula here, so since we are starting with maximum displacement, our x versus time is going to be as far away positive as possible. Then it's going to pass through the equilibrium. It's going to go to maximum negative displacement, back to the equilibrium, and then back to the positive. So we're definitely going to be working with the cosine of this one. So where is it going to be located? So amplitude is what's the farthest maximum displacement away from equilibrium. It's going to be 20 centimeters. And then we got our cosine of our 2 pi. Now here's the thing. You must remember, since that's 2 pi, that's in radians. You must use radians. Make sure your calculator in the mode is set to radians. If you have it set to degrees, you're going to get very, very different answers. So make sure that this sucker, when you're using these equations, they have to be in radians. It won't work in degrees. And remember, that's true because we always been working with radians in any calculation. Times frequency. Our frequency is 0.71 times our time period that we want to know. So we're looking for where is it going to be after 2 seconds. So multiplying this all out, and again, I'm thinking it's going to be on its way back to equilibrium, or at least in that roundabout area. 20 cosine of 2 pi, or 6.28, times 0.71 for frequency, and after 2 seconds, it's going to give you a value of negative 17.5. So actually, it's moved its way past the equilibrium point at the 2 second mark, and it's on the way basically to reaching the negative direction here, a little bit further than I anticipated, but negative 17.5 centimeters is going to be the location at the 2 second mark in this particular case. So let's go ahead and try this for a pendulum system.